Hello, welcome everyone. This is Suresh Kothari. Thank you for listening to my talk. This is the last segment. We have discussed how to verify safety and security properties using the algebraic method. We compute CRS, then we map CRS to CRB, and then we apply a homomorphism to get a reduced algebraic expression from CRB, which represents just the relevant execution behaviors, and we can use that reduced expression to verify a safety or security property. We looked at two examples. One was division by zero vulnerability and the other was lock not followed by unlock vulnerability. In both examples, it was enough to examine one function. In general, we will have to examine many functions to verify a vulnerability. And that is what we are going to discuss in this segment. Again, the basic idea is to apply homomorphism. However, there are many technical details, and so although in slides the topic of multi-level function sequences appears under homomorphism, I've kept it to the end in this video presentation. The key idea is a multi-level function sequence which is defined here. A direct call is a call at level 1. We will start with a simple example first. Now let's illustrate the multi-level function sequences using this example. It's a simple example. It includes a nested function call to unlock from F to F1, from F1 to F11, and from F11 to unlock. It's a three-level nested call to unlock from F. In F, we have lock followed by F1. If we just look at the execution behavior of F, lock is not followed by unlock. So in order to get the unlock which happens inside F1, we must use multi-level function sequences. So without multi-level function sequences, we can get erroneous vulnerabilities. The function calls are shown here by a call tree. F calls lock followed by F1. F1 calls F11, that is shown by a dotted arrow because it is a conditional call. The call to F11 happens if condition C is true. So the way we compute multi-level function sequences, there are two important things to keep in mind. One is we apply homomorphism using function calls as the relevant statements. So we compute the first level function sequences using the homomorphism. So to get the first level function sequence for F, the relevant events are calls to lock at program statement 2 and call to F1 at line 3. And as before, we compute the execution behavior. We get the function sequence lock followed by F1. Okay. The second thing to keep in mind while computing multi-level function sequences is we compute a function sequence and then we substitute the function sequence of the called function into its caller to get multi-level function sequence. Now let's first look at all the first level function sequences. For F we have lock followed by F1. For F1 we have F11 plus 1m. Since the call to F11 is conditional, if condition is true we get the sequence F11. If the condition is false, we get the null behavior which is shown here as 1 sub m, the multiplicative identity. The function sequence for f11 is just unlock. And now we substitute the function sequence from one function into another. So we substitute the function sequence for f1 into f, and we get the function sequence lock followed by f1 square bracket f11 plus 1 m. So the notation square bracket is used to show that it's a called function. So f11 is a function called from f1. Okay. And by doing these substitutions, we eventually get the function sequence, the three-level function sequence for f. It is shown here. Let's now illustrate how to count the number of multi-level function sequences. We have looked at how to derive the multi-level function sequences for this simple example. So we have the first level function sequence for f, which is log followed by f1. Then we have the second level function sequence for f, and then the third level function sequence for f. The number of function sequences are computed again using the properties of the algebraic expression. In this case, we have in parentheses two terms, and each term would correspond to a function sequence. So we are going to get two function sequences. They are shown here. One function sequence is log followed by f1 in square bracket f11 in another square bracket unlock. And keep in mind the square brackets reflect that it is f11 is called by f1 and unlock is called by f11. So the called relationship is reflected by the square brackets. Now let's count the number of function sequences for a loop. So we have a loop here with function calls g1 and g2. Those are the relevant statements. Given the CRB for the program, we apply the homomorphism with the program statements 8 and 12 as relevant statements. We get this reduced CRB for relevant execution behaviors. In this case, the relevant execution behaviors are function sequences, and we get this algebraic expression for the function sequences. So this algebraic expression, again we can count. There are three terms here, so we are going to get three behaviors, but each of this behavior we are going to count twice, because we have the loop g1, g2, and either we will have at least one complete iteration or no iteration. That's why we will count g1, g2 star as 2, and so we get this 6 function sequences for this example of a loop. We will now illustrate the use of multi-level function sequences for verifying a safety property. For the function dgWrite from the Xenu operating system, the safety property that we will verify is that the call to get buff, which is memory allocation, is followed by a call to free buff, which is memory deallocation. The inside dgWrite, after the call to get buff, free buff is called, but there are other paths on which the pointer to the allocated memory is passed to function UDP send without the free buff. So we must examine the function sequences that get generated from UDP send to check whether the call to get buff is followed by free buff. This example has another complexity. We see that from dgWrite, the function make ARP gets called, and make ARP makes another call to get buff. So really we have two calls to get buff, and they must be kept separate while we are matching a call to get buff by free buff. Without the help of algebra, computing the multi-level function sequences for this example would be practically impossible. The number of multi-level function sequences for DG write is 10 to the power 58. So one thing that we did is that instead of computing all the multi-level function sequences, we first determine the relevant functions and then compute the multi-level function sequences only for the relevant functions using homomorphism. So the idea of homomorphism again becomes very important for verification. Without it, we have an enormous task of verifying 10 to the power 58 multi-level function sequences. By restricting to the relevant functions, we get just 83,890 function sequences instead of 10 to the power 58 function sequences. The algebraic expression which gives us the 83,890 function sequences is shown here, and later we will get into the derivation of this algebraic expression. Okay. The human-machine collaboration is also important here. There are several complexities here. As we mentioned, there are two calls to getBuff and they must be kept separate. But the another complexity is that there is a call to a function write and the pointer to the allocated memory is passed to another function through write, but it is not called directly, it is called through a function pointer. So we need to resolve the call to the function pointer. But as a human, we decided that instead of clubbing the two difficulties together, we can first analyze the problem without taking into the call to the function pointer, and then later on take the call to the function pointer into account to do the complete verification. Now we will explain how the multi-level function sequences get computed. One thing we had mentioned was we compute a first level function sequence for, and then we substitute it in the caller. So for example, the get address gets called from different functions. It gets called from get path, it gets called from IP send, it gets called from getNet. So we have to substitute the function sequence for get address in different places where it is getting called. Moreover, a function may get called in multiple places in another function, and we have to keep track of the call sites. So here are the call sites. So in this case, we show the different call sites. We can see that the function getPath is getting called in two different places in function route. So when we are substituting the function sequence for getPath in route, we have to substitute it in two different places in route. The total number of call sites in this example is 19. Now, doing this by hand would again be practically impossible. So the computation of multi-level function sequences is done automatically. This information about call sites is generated by Atlas, and the utility that we have built for computing multi-level function sequences takes advantage of the capabilities that Atlas provides, such as keeping track of the call sites. So here is the actual graph from the Atlas which shows us the different call sites. The 19 call sites are shown here. Now, to illustrate the computation of multi-level function sequences, we take different chunks and illustrate the computation for each chunk, and then we put the things together. So here first we will illustrate the computation of multi-level function sequences for the function getAddress. So getAddress calls sndArp, sndArp calls makeArp, and it calls write. So it's a two-step process. We are computing the function sequences for each of these functions, and then we are going to substitute the function sequences from one function into another function where it is getting called. Now, some of the functions are treated as atomic functions. So for example, we are treating write as an atomic function. As I mentioned earlier, write has a function pointer call, and we decided that we are going to deal with that later. The other function is getBuff. We don't really need to analyze the functions which are called from getBuff. Because after all, we are trying to match getBuff with freeBuff. We are not concerned with what happens inside getBuff. So here is a call graph that tells us that getAddress calls sndArp, sndArp calls makeArp, and then getBuff and write are going to be treated as atomic functions. So in the next few slides, we'll see that we are computing the function sequences for makeArp, sndArp, and getAddress, and we are going to substitute those function sequences from makeArp into sndArp, from sndArp into getAddress. The computation of function sequences is again done using homomorphisms, as we illustrated through a simple example. So for the function getAddr, we have this CRB, and then we apply the homomorphism and we get the reduced algebraic expression, which gives the first level function sequence for sndArp. We do the same thing for sndArp, and we get the algebraic expression for the first level function sequence for sndArp. And then we also get the first level function sequence for makeArp. It's simply getBuff. Then we do the algebraic substitutions. So for example, we take in getAddr, its function sequence is sndArp plus the 1 sub m. Now we substitute the function sequence for sndArp into getAddress. So this is the first level function sequence for sndArp that's substituted in getAddress, and we are using the square brackets to reflect that. For example, getAddr calls sndArp, and then sndArp calls makeArp. We are not showing the square bracket for write because we are treating write as an atomic function, and we are not going to generate function sequences for write. Okay, so eventually we get this algebraic expression for multi-level function sequences for getAddr. Now if we count the number of multi-level function sequences for getAddr from the algebra, we can see that there are 3 terms here, and so the number of function sequences or the number of terms that will be generated is 3, and this is a loop here, and as we mentioned earlier, when it is a loop, we count it as two. One, either the loop completes an iteration or it's not entered. So the total number of function sequences that we are going to get is, when we do the multiplication, we are going to get 2 times 3 and then plus 1 here for this term, which is multiplicative identity. So the total number of function sequences, the multi-level function sequences for get ADDR is 7. We computed the multi-level function sequences for the chunk which consists of the function get ADDR, SND MK and write. Now we will do the same for the second chunk, which consists of the functions route, getNet and getPath. The functions getADDR and MKARP get called by getNet, getPath, etc. So when we are computing the multi-level function sequences for route, we will make use of the result we have already computed for getADDR and MKARP. The process is similar. We compute the first level function sequences and then we do this substitution. So here we are computing the first level function sequence for route. Then we have the first level function sequence for getADDR. And we have substituted the first level function sequence for getADDR in getNet to get the algebraic expression for the multi-level function sequences for getNet. If we look at the algebraic expression, we can see that the number of function sequences for getNet is same as getADDR, which is 7. Then we get the first level function sequence for getPath, and it has getADDR, MKARP, write, and we already know the algebraic expressions for the multi-level function sequences for them. So we are going to substitute those to get the first multi-level function sequence for getPath. So here is the algebraic expression for the multi-level function sequences for getPath. Again, using algebra, we can easily count the number and we get that there are 29 multi-level function sequences for getPath. Finally, we come to route. We have this first level function sequence for route, and using that we can easily count the number of multi-level function sequences for route, because we know the number of multi-level function sequences for getNet, getPath, etc. And again, using algebra, we get that the number of multi-level function sequences for route is 11,984. Here we have shown the algebraic expression for multi-level function sequences for route. Now we'll finish the computation for DG write. We have the last chunk, which consists of DG write, UDP send and IP send. And while computing the algebraic expression for this chunk, we'll make use of the algebraic expressions we have already computed. For example, the algebraic expression for route will be substituted when we compute the algebraic expression for IP send. The process is very similar. We compute the first level function sequences and substitute the results. Now, if we look at the expression for DG right, we can compute the number of function sequences for DG right. It can be easily done using the known results. We know that for get ADDR, the number of function sequences is 7. For route, it is 11,984. And then by doing the algebra, we get that the number of function sequences for DG right is 83,890. The DG right calls 36 functions, of which the homomorphism retains 12 as relevant functions. The 36 functions have altogether 89 call sites, of which 19 call sites are for the relevant functions, which are taken into account by the homomorphism. And the net result is pretty significant. From 10 to the power 58 function sequences, we go to 83,890 function sequences, and we get this compact expression for the multi-level function sequences for DG right.